Okay, looking at some more right triangle trig applications here. And for each one of these, before you watch any of my instruction on it, please try it yourself. Please read the problem. Do as much as you can with it. If you want to skip ahead, if you want to take a look at my answer first, that's okay. But it's going to be to your benefit if you give each one at least the setup, at least a try before you go. So parallelogram ABCD has vertices as listed. Determine the measure of one of its larger angles. So I've already plotted this, and you can plot it as well just by using the correct coordinates. One of the larger angles would be either A or C. And so if I just drop a perpendicular down within the parallelogram, I'm going to get a right triangle that I can use for solving angles. Now, I'm trying to solve for A, right, or C. So in order to do that, what makes the most sense to me is to use these two side lengths, which I just simply counted on the grid, 7 and 5, to solve for angle D. And then once I know angle D, I'll know the acute part of angle A, and I can just add 90 to it. Also, angles A and D are supplementary because it's a parallelogram. So let's go through this process. So I'm focusing on triangle AD, I don't know, we'll call it E. It's a terrible triangle. Hang on one second. Let me just fix that. Okay, so slightly better. So there's angle A, angle D, and we'll call this E for now. Put it in the diagram. Okay, there's a 5 here. There's a 7 here. And I want to know what angle E is, so that's my theta. Okay, so let's see. 7 is opposite from theta. 5 is adjacent. Still labeling O and A after all this time just because it helps me so much setting up my trig ratios. Tangent for O and A. Tangent of theta is equal to 7 over 5. So theta must be inverse tangent of 7 over 5. And I'm getting about 54 degrees for that. And so that's here, which tells me that angle A is 180 minus 54. So angle A must be about 126. I could also use the right triangle part of it, and that would give me 36 here, which plus 90 also equals 126. All right, so anytime you have a diagram like this, try to figure out where there's a right triangle, because your trig is going to be able to solve for right triangles. All right, rhombus DEFG, common length side is 18. Put that all around. Okay, so this is DEF G. As long as you go around it clockwise or counterclockwise with those letters, you're good. Just don't want to skip across. Okay, the smaller interior angle has a measure of 68. Let's call that this one. That looks like the acute angle. Okay, and what is the length of its longer diagonal? So that's going to be this DF segment. So let's just go across from D to F. Hopefully you did a better job than I just did. All right, so that 68 splits into a 34 and a 34 because rhombuses have that property that the diagonal splits the angle in half. So what's the length of the longer diagonal? Okay, well, let's see what I can do here. What if I draw the other diagonal too? And this time I'm just going to use the line tool so that I don't make a mess of it. Okay, if I draw that in too, then I have a right angle right here. Let's call that point H, just so I have something to refer to it. So triangle EHF is something like this, with an 18 on the EF segment, with a 34-degree angle, and a right angle. Okay, well, I can solve for a segment FH, which would be nice because that's half of my diagonal that I'm looking for. So I'll put an X there. And so within that mini right triangle, 34 degrees, X is the adjacent side, 18 is the hypotenuse, A and H tells me to do cosine. Cosine 34 equals X over 18. So that's pretty easy. That X is going to be 18 times cosine 34, which is approximately 14.9 inches, which means that my DF segment, which is 2 of those, is going to be approximately 29.8 inches. Okay, so once you figure out where the right triangle exists, the trig is simple. You just solve for that missing piece and then you go. All right, exercise 3. Regular pentagon is shown with F at its center. In other words, point F is located so that all 5 of these spokes are equal. Now that only happens in a regular polygon, but since this is a regular pentagon, we're good there. So each one of these is essentially an isosceles triangle with side length 4. Let's see if I can get that drawn quickly. There's my cheating shape tool. All right, so that's a 4 and a 4 for, we'll call it, let's use just this ABF. So there's A, there's B, there's F, and it's a 4 and a 4. And I don't know what this side is, but actually determine if the pentagon's perimeter is more or less than 2 feet, so 24 inches. Well, that means that I need to know what this outer side is, right? Because if I know what that is, since it's a regular polygon, there's 5 of them. If I know what x is, then I can multiply by 5 to see whether it's more or less than 2 feet. Okay, well, we know what to do with isosceles triangles, right? We drop a perpendicular down. And as of right now, I don't have any angles. We need to do something about that. This point F, if I go around to all 5 of these angles, I get a circle. Every circle contains 360 degrees. So all of the angle F's are going to be 360 divided by 5, because there's 5 of those angles. So that comes out to 72. That's called a central angle. That central angle is 72 degrees, which is what angle F was. And so since I dropped a perpendicular here, let's just split that 72 equally, with 36 on each side. Why do I want to do that? Well, now I've got a right triangle here. And so I can solve that, right? So I'm interested in x. So let's split that x into a pair of equal unknown sides. Let's call them both y. If I can solve for y, then I can just double it, and then I'll have x. Okay, so let's see. That y is opposite from the 36, so we'll go an O there. The 4 is the hypotenuse, right? Because, yeah, across from the right angle, so that's my h. So I'm doing a sine problem. Sine 36 is equal to opposite y over hypotenuse 4. Okay, so 4 times sine 36. And that comes out to about 2.35, which means that this x segment, that's the y, my x segment must be double that, or about 4.7, because I took half of the triangle when I did the sine equation. So if the x is 4.7, then the perimeter of the pentagon must be about 5 times 4.7. So that's about 23.5 inches, which is less than 2 feet. Just a little bit, but it's less than 2 feet. Okay, next page. All right, we've got this tower problem. And we're 327 feet between the tower and the building. A person from the second story measures an angle of elevation. So again, that's looking up from the second story, 32 degrees. Angle of depression, again, looking downward from the horizontal to the bottom, to the ground, at 18 degrees. Find the height of the tower to the nearest tenth of a foot. So instead of taking the entire height, I've split it into an x and a y. X for the top half with the 32-degree angle, y for the bottom half. Try this problem yourself. See what you come up with. Okay, so my x is my opposite side. My 327 is my adjacent side. Opposite and adjacent tells me to use tangent from 32. Tangent also from 18 because y is opposite from 18 and 327 is adjacent to it. So I've got a pair of tangent equations. Solve them both. Put them into the calculator and add them together. 310.5 is my final result. Okay, so that's the first one. You can pause, take a second to process that, but we have a pair of right triangles here with opposite over adjacent, so tangent's going to work. All right, and then exercise 5. See if you can set this one up. Okay, we're flying a kite. We originally let out a line of 232. That's this position. We let it out further, the kite rises. That makes sense. So the kite at point C is higher than it was at point B because I let out more line. So we want to figure out, ultimately, how much higher the kite is at C than it was at B. So what I've got to do is figure out where that distance is, that difference between them. So I just let it be x. Now, this is not a right triangle here where the x is. However, if I can figure out what AC was and subtract the bottom triangle, so if I take the outer triangle minus the inner triangle, in other words, AC minus AB, then I can get that missing distance here. So what I'm going to do is solve a 48-degree triangle and then solve a 53-degree triangle and see where that takes me. All right, so let's take this AB segment, let that be a y. Well, I don't know, I'm not exactly sure what variable I use. I think I might have just kept it as AB. Yeah, so if I keep it as AB, that's my opposite side from 48. My hypotenuse is 232, and so I can solve for AB. When I shift over to the 53-degree angle, now my opposite side is AC all the way up. So I'm just going to take that out. I'm not actually using a y. Okay, now I shift it to the 53-degree angle. I'm at AC. Hypotenuse is now 258. So solving those equations gives me 172 and 206. Right? And so all I need to do now is subtract the bigger minus the smaller, and I get my BC segment. So take a second to copy that down as well. We will do several more problems just like this. These are a little bit more challenging than the previous set were, but hopefully that works out for you.